Alright, welcome back. So in this video we are going to do 3 examples using the ratio test, one that is in each of the categories for either convergence, divergence, or being inconclusive. So as a reminder, this is the ratio test. It says that given an infinite series, we can determine if it converges by looking at the ratio of subsequent terms. If that ratio is less than 1, then we have convergence. If it's greater than 1, then we have divergence. And if it's equal to 1, then it's inconclusive. Okay, let's work through some examples. So a lot of this is just setting up the problem and then manipulating things algebraically. So we're going to be doing that a lot of times here, just keeping track of lots of variables and simplifying them so we can take a limit. So first, let's consider the series from n equals 0 to infinity of n cubed over 4 to the n plus 2 power. So we're going to look at the subsequent terms, a sub k plus 1 over a sub k. Okay, so I'm going to substitute in k plus 1, and then I'm going to divide it by what happens when I substitute in k. Now I just need to simplify. I like to multiply by the reciprocal first, and then I'm going to figure out what I can cancel. So here, I'm noticing that 4 to the k plus 3 power is like 4 to the k plus 2 plus 1. And so I'm going to split that up into 4 times 4 to the k plus 2. So it's often common to split up the things with the powers so that we can cancel them out. So I'm basically trying to get a 4 to the k plus 2 there in the denominator so I can cancel it out. For now, I'm just going to leave my k plus 1 cubed and my k cubed. So by doing this, I'm canceling out my 4 to the k plus 2's, and I'm left with k plus 1 over k cubed. I'm putting that cubed on the outside. And then I'm going to multiply by 1/4. That's what's left over in that second part. Now I've combined these two cubed things together so that I can simplify them. This is really k over k plus 1 over k, all cubed, times 1/4. K over k is just 1, and then I have plus 1 over k. So the limit I'm going to look at is 1/4 times 1 plus 1 over k cubed. So when I look at the limit as k approaches infinity of the absolute value of r is what I just found. All of this is positive as k grows to infinity, so I'm not going to worry about my absolute values. So I'm looking at the limit as k approaches infinity of 1/4 times 1 plus 1 over k cubed. Then as k approaches infinity, that 1 over k goes to 0, so I really just have 1/4 times 1 plus 0 cubed. 1 cubed is just 1, and so I get 1/4. 1/4 is less than 1, meaning this series converges. Okay, so all that really took was just some algebra to simplify things, and if it's been a while since you did exponents or had to keep track of this sort of stuff, it might take a little bit of time to get used to it again. But the techniques we do tend to repeat themselves for ratio test. Okay, let's do another example. So this time let's consider this series n equals 1 to infinity of n factorial over n cubed. Just as a comment, I started the series at n equals 1 since we can't divide by 0, so I couldn't have n equals 0. Okay, so to determine convergence here, we are going to look at the ratio of a sub k plus 1 over a sub k. So first I'm substituting in k plus 1 for n, and I'm dividing it by what happens when I substitute in k for n. Then my whole goal is to simplify this and send k to infinity, so I'm going to simplify and cancel some things out. I'll multiply by the reciprocal here, so I'm multiplying by k cubed over k factorial, and I'm hoping things cancel out. So with the k plus 1 factorial, this is a trick we did before when we had factorials in the previous video. I'm going to rewrite k plus 1 factorial as k plus 1 times k factorial. So I'm sort of separating out the first term, the k plus 1, and then leaving the k factorial left out. Then I can cancel my k factorials, and I'm also going to be able to cancel that k plus 1 with one of the k plus 1's in the denominator. So I'm left with k plus 1 squared in the denominator and just k cubed in the numerator. Now let's take the limit as this as k approaches infinity. So we do the absolute value, but here as k approaches infinity, these are always positive, so I don't worry too much about those absolute values. Then looking at this, I'm noticing that I'm in an infinity over infinity situation. So you might have a couple options here. I like to use L'Hopital's rule to show my work, or you might just look at this and see, okay, k cubed in the numerator is going to grow faster than k squared in the denominator, So this is going to go off to infinity, since k cubed is going to grow faster than k squared. But to do this formally, I will do L'Hopital's rule. So I'm taking the derivative of the numerator, that's 3k squared. The derivative of the denominator is 2 times k plus 1. Then I'm still in L'Hopital world with this indeterminate form, so I need to do it again. I'm getting 6k over 2, which as k approaches infinity, this is growing off to infinity, and so this limit does not exist. Therefore, since we are not at a value less than 1, this series diverges. All right, let's do one more example. So again, this process is going to follow very similarly. This time I'm doing the series from n equals 1 to infinity of 1 over n squared. Looking at subsequent terms, I plug in k plus 1 for n and divide it by what happens when I plug in for k. Then I multiply by the reciprocal, k squared over 1, and I'm going to just distribute the k plus 1 squared in order to get something that looks a little simpler. So I have k squared over k squared plus 2k plus 1. Now I need to take the limit as k approaches infinity of this value, of this ratio, and so absolute values, they don't matter too much here since everything is positive again. Then looking at this, I could use L'Hopital's rule since I have infinity over infinity as my indeterminate form, or you might see that these are growing at the same rate. So k squared and k squared plus 2k plus 1 grow at the same rate, and so this is going to go to 1. 1 is going to be the solution to my limit, but if you need to use L'Hopital's rule to get there, that's fine too. So I take the derivative of the numerator, that's 2k. Derivative of the denominator is 2k plus 2. I'm still in infinity over infinity, so I need to do it again. I'm getting 2 over 2, which doesn't have any k's left anymore, so we just have 1 as our limit. Now in this case, 1 isn't less than 1, so we're in that inconclusive case. We're not greater than 1 or less than 1, we're equal to 1, and so this ratio test doesn't tell us anything about this series, and we need another method in order to determine what's happening here. Okay, so that is 3 examples, one for each of the cases. We did a convergence case where r was less than 1, that is, the absolute value of r was less than 1. We did a divergence case where the absolute value of r was greater than 1, and we did a case where it was inconclusive because it was equal to 1. Hopefully that gives you a little more confidence with how the ratio tests works. Thanks so much for watching, and I will talk to you in the next one.